Okay, so now we're going to talk about the situation. What happens if we allow p to be a more general number? Like, for example, what if we did -4, choose 3? -4, choose 3. Well, that's going to be over 3 factorial, right? So 3 times 2 times 1, because that's, again, the formula goes down to over k factorial. So, and then just like before, you're going to have 3 terms. This is going to go down to be -4, drop it by 1, drop it by 1 again, so that you get to a number that's 1 more than p minus k. -4 minus 3 is -7, and we're 1 more than that. So it's a little different. Unlike the positive coefficients, right? We don't have that worry about 0 slipping its way in there, since we've already started underneath, and we're just going to keep going underneath. So it actually doesn't matter whether that number, obviously 3 is smaller than 4, but even if we wanted to make a 5 there, we could still do it, right? -4, choose 5. We just have 5 terms on top, and then 5 factorial on bottom. Okay, so we can multiply that out. Well, or think of it this way. The 6 will cancel with the 3 times 2, and then we have 3 negatives on top. So that'll all multiply out to be -20. -20. Okay, so that's a binomial coefficient when p is not a positive integer. It can be a negative integer. It can even be a fraction, as we look at the next example. We have 1/2 choose 4. 1/2 choose 4. Well, on the bottom, that's going to be 4 factorial. 4 times 3 times 2 times 1. And we're going to have 4 things on top. That's how I always remember it. Don't ever work out that p minus k plus 1 thing. I don't worry about that. I just realize however many things I have on the bottom, that's how many I'm going to have on the top. So I would start with 1/2, and I keep dropping it by 1. So -1/2, -3/2, finally -5/2. Okay. And then we work that out. So on top, I'm going to have -15 over 16, and then that's all divided by 24. All divided by 24. And then simplify that. That's going to be -15 over 16 times 1 over 24. 3 will cancel with the 24 to leave us with a -5 on top. When you take 3 out of 24, you're left with an 8. 8 times 16 is going to be 1/28. So 1/2 choose 4. We have as a number there -5 over 28. And so now it turns out with these extended binomial coefficients, if you will, we can actually talk about now what's called a binomial series. Binomial series. And that is the sum as k goes from 0 to infinity of binomial coefficient pk x to the k. And it turns out that will be equal to 1 plus x raised to the p power, provided that the absolute value of x is less than 1. Okay. We're not going to prove that or anything. We're not going to go through the work of proving that. But we're going to take that kind of as a fact. Without going through the trouble of proving it. But it turns out this thing here, this binomial series, will converge to 1 plus x to the p when the absolute value of x is less than 1. Okay. Otherwise, it will be a power series that diverges. And so basically the binomial series is just taking and saying, hey, let's let the limit go to 0, which in a binomial would actually just, if k got bigger than p, then all those terms would just be disappearing anyway. They all be 0. So we could actually let that go to infinity, and it would still just be this thing because all the other terms would have zeros in front of them. And so we're letting that idea continue, and it turns out this thing does converge, provided the absolute value of x is less than 1. The absolute value of x is less than 1. This will turn out to be a convergent series, and it will actually converge to 1 plus x to the p, where p now, again, does not need to be a positive integer. It could be, as we saw in the first example, it could be a negative integer, like -4, or it could be a fraction, like 1/2 here. Okay. That's known as the binomial series. We're going to look at an example or two with the binomial series here in just a moment.